The first part of this lesson deals with derivatives of other trig functions. We already saw that the derivative of tangent of x is secant squared, and this gives a few of the other ones. So we're going to find the derivative for part A, g prime of x. The derivative of x is 1. Derivative of tangent is secant squared. That's it. Okay, this one, I'm going to use the product rule. You could write dy dx or y prime. The derivative of x is 1, so I don't have to write that. I will just so you see it. Times secant of x plus x times the derivative of secant, which is secant x tangent x. And that's it. Okay, the first one, we're going to use the quotient rule. And let me just point out, 1 over, if I break this up into two fractions, we get the same function we have here. So the derivatives should also be equivalent, and we're going to show that. So I'm going to get a smaller pen here. All right. Remember to sing your song when you're taking this derivative. Ho dee high minus high dee ho. All over ho ho. Okay, we know we're going to have to find equivalent derivatives, so we should probably start simplifying a little bit. Oops. Oh well, sine squared of x minus 1 times cosine of x plus cosine squared of x. And that's all over sine squared of x. Sine squared plus cosine squared, that's 1. So we have 1 minus cosine x over sine squared x. Because I know the next one's in two terms, I'm going to break this up into two terms. So I have 1 over sine squared of x minus cosine over sine squared of x. And I'm going to write it like this, sine. Okay, so let's try the other problem. This one should be a little bit easier if you know your derivatives. Derivative of cosecant. Negative cosecant x, cotangent x. And the derivative of cotangent is negative cosecant squared. So we're going to end up with positive cosecant squared. Okay, right now it doesn't look like what we have, but wait. Okay, let's rewrite it in the same order. We have cosecant squared x minus cosecant x cotangent x. Cosecant's the same as 1 over sine squared. That's good. We got that part. Okay, cosecant is 1 over sine squared, or sine, and cotangent is cosine over sine. So those are equivalent derivatives because they were equivalent functions. So sometimes you might want to use the quotient rule, and sometimes you might not. Okay, so you might want your answer in this form if you're trying to find zeros or undefined locations. Okay, you might want your answer in this form if so it's easier to take the derivative again. So it depends on what you're comfortable with. As we keep going, okay, higher order derivatives, you would write it like this. Okay, this is something, it changes at the fourth derivative if you're using the prime notation. Okay, and then this isn't so bad. Okay, it's just different ways to write it. So that means an example 8 to find the fifth derivative. So we're going to start with the first derivative, y prime. That wasn't so hard. Okay, y double prime. Y triple prime. Use the correct notation. Okay, the fourth derivative. Oh, I keep writing too many lines. Okay, the fourth derivative there, 0. And so the fifth derivative, also 0. Well, this is a good problem. So let's see if we can find any patterns here. Derivative of sine is cosine. So let's say, what's the second derivative of sine? So that would be the derivative of cosine, which would be negative sine. The third derivative, negative cosine. And the fourth derivative would be sine. If you take the fifth derivative, that pattern's going to repeat. So I want you to write the answer to this problem in your whisk. Example 10. We have a table instead of functions, which you're going to see pretty commonly. And we have this function, we need to find the derivative. So let's start with just the derivative of the basic function. So we have ho d high minus high d ho all over ho ho. Now instead of x, we're going to plug in 0. Just trying to save space there. So h prime of 0. G of 0, look in your table. G of 0 is 5. F prime of 0 is negative 3. F of 0, 2. G prime of 0, negative 1. And then G of 0 is 5 squared. So simplify that, we get negative 15 plus 2. So it'd be negative 13 over 25. And there you go, it's not so bad. Now this is fun, because look, we have a triple product. I told you it was coming. Okay, so this is pretty exciting. I'm going to make a little bit of space here so we could write it all out. I want you to see it clearly. I'm going to try to use different colors for you. Okay, x is going to be in green, f of x is in blue, and g of x is in purple. So when we are going to find h prime of x, you just have to make sure you get the derivative of each part. So I'm going to start with the first one, and then I just write the other two. Okay, plus. And notice I'm just changing which one. That should not be a dot there. There we go. Which one is being taken, or which one has the derivative being taken? Okay, so see that in the first one, the derivative was of x. In the second one, the derivative was f of x. And in the third one, the derivative was g of x. And then the other ones, you just leave them the same. So it's not so bad. Now you're just going to be plugging in numbers. So we're trying to find h prime of negative 1. So f of negative 1 is 3. G of negative 1, negative 2, plus negative 1 times f prime of negative 1. 4. G of x, negative 2. Okay, and then we have negative 1, 3, and 2. We could leave it like that, but we're going to evaluate it and simplify. So we get negative 6 plus 8 minus 6, negative 4. And there you go. Okay, last problem here. So we're trying to figure out how many times stronger is the acceleration due to gravity on Earth than it is on the moon. The position function, h of t, is given. So remember that h prime of t gives us velocity, and h double prime of t gives us acceleration. So the acceleration due to gravity, we have to find the second derivative. So if h of t is this, h prime of t, or v of t, be negative 1.6 t. And then h double prime of t, or v prime of t, or a of t, would be negative 1.6. And this would be feet per second squared. So this would be the acceleration due to gravity on the moon. Acceleration due to gravity on the Earth, maybe you learned that in physics, maybe you didn't. Oh, I put feet. Okay, good thing. Meters. We don't want to have to do conversions. On Earth, it's about this. So, about how many times stronger is that? That's about 6 times stronger. So, what would your weight on the moon be if the acceleration due to gravity is about 6 times stronger on the Earth than it is on the moon? All right, have a good day.